Welcome back, guys. Now in this video we're gonna talk about the procedure for the application of equation of motion sum of forces is equal to ma. How to do this? What are the steps? The first step ever is to select the convenient inertial coordinate system to apply the sum of forces equal to ma equation. And it's up to you guys to select what is this convenient inertial coordinate system. It could be rectangular components, normal and tangential, or cylindrical coordinates. Of course, guys, if this is a rectilinear motion, I should use the rectangular components. If it is a curvilinear motion, I can use the normal and tangential or cylindrical coordinates. Then, I should draw the free body diagram showing all external forces applied to this particle or to this body. And I should, of course, resolve forces into their appropriate components. For example, if I am using the rectangular components, I should, in fact, resolve the forces in x, y, and z directions. Then, I should draw the kinetic diagram showing the particle's inertial force ma. So after finding the resultant force, ma will be equal to this resultant force so that I can find out what is the direction and what is the magnitude and what is the sense of the acceleration a. Alright? And then, guys, I'm going to apply the equations of motion in their scalar components, like sum of fx is equal to max, sum of fy is equal to may, sum of fz is equal to maz in rectangular components, or sum of ft is equal to mt, sum of fn is equal to man, and so on. And of course, guys, it may be necessary sometimes to apply the proper kinematic relations to generate additional equations. For example, guys, if I want to know what is AT, and I know, guys, that the equation of AT could be found from the kinematic relations from chapter 12. So I can use this equation in order to know the value of AT and to put it in the equation of sum of FT is equal to MAT. So you're going to use the relations of kinematic equations. If I am at Kinetics chapter, this doesn't mean, guys, that I have to forget about the kinematics relation. No, because in fact, I can use these relations in order to get rid from one unknown or in order to solve for my system. So let's start, for example, by defining the rectangular components. I know that the sum of forces is equal to ma is a vector equation. So if I want to put it in a scalar form, let's say I am in 2D, guys. If I am in 2D, so I only have two directions, x and y, I can put this sum of forces equal to ma in a scalar form. For example, I can say that the sum of fx is equal to max and the sum of fy is equal to may. Now maybe, guys, I know that there is no acceleration in x direction because in fact the velocity in x direction is always constant, so I can get rid, for example, from this term, and in this case I am using the kinematic relations. Or I know that ay, or I know that the acceleration in y direction is constant, and this means that I am here at a uniformly accelerated motion, so I can also use the equation of uniformly accelerated motion from kinematics chapter in order to solve for the system. Now, if I am at a 3D case, or if I don't want to convert this equation into scalar form, I can use the vector form equation, all right? So I can, for example, sum up these forces in vector form, and in this case, A resultant, A here, will be, of course, AXI plus AYJ plus AZK, all right? So it's up to you. How do you want to do it? You can do it in vector form or you can do it in scalar form like this case here. Now, what is the free body diagram? As I said, guys, the free body diagram is the diagram that shows only the external forces. I'm not interested with the internal forces because, in fact, their sum is equal to 0. So always, guys, the free body diagram is the body diagram that establishes only the external forces. These external forces usually include the weight Right, so the weight which is always vertical and it's equal to m times the gravity, the normal forces that is always that are always perpendicular to the area of contact, the friction forces that are always opposite to the motion, and the applied forces like here, the towing force P is equal to 400. So this is also an external force, and this is maybe that is causing this motion of this body. So if I want to show the free body diagram, and this is a very important step, because if I have any mistake in this free body diagram, this will be reflected in the equation of forces or in the equation of motion. So what are the forces exerted here on this body? What are the external forces exerted on this body? I have, of course, the friction force that is equal to the constant of friction times the normal force. I also have the normal force, and I have this external force, the towing force, that is equal to 400 newtons, and I also have the weight. Now, if you do the resultant force, you can see, guys, that this resultant force is not equal to 0, which means I'm not in statics. I'm not at the first law of Newton. I am at the second law of Newton that states that the sum of forces is equal to ma. So I should find out what is this resultant force, and then I have to show the inertia force, which is equal to ma, and this a is a vector that has the same direction, the same sense, and that is proportional to the resultant force. This is ma, all right? So guys, make sure that any friction forces, as we said before, act opposite to the direction of motion, and if the particle is connected to an elastic spring, a spring force equal to kx, as we said before, this should be included on the free body diagram. So guys, the first step is to indicate the inertial coordinate system. The second step is to show the free body diagram as well as the inertia force. F is equal to ma. That should be collinear in the same direction, the same sense of the resultant force. And the third step is now to apply Newton's second law that states that sum of F is equal to ma in your chosen coordinate system. For example, if it is a rectangular component system, you have to show it in a Cartesian vector formulation like ijk, or in a scalar formulation like xyz. If it is normal tangential binormal direction, you have to show, of course, un, ut, ub, an, at, ab is always equal to 0. Or in a scalar like in normal direction, in tangential direction, and then in b normal direction. Now, if it is in cylindrical coordinates, same, you have to show it in ur, u theta, uz. You have to write down this equation of motion in these components. Now guys, sometimes, as we said, you have to use the kinematics relation. For example, if the question is to find a certain force and you can find it from the kinetics equation of motion, you don't have to go back to the kinematics relation and then to write down the equation of acceleration, velocity, and position. However, sometimes the question is to find the velocity. Alright, so how to find this velocity? I have to find first the acceleration. How to find this acceleration? I have to put the equation of motion on Newton's second law. So you have to put Newton's second law, find this acceleration, and then from this acceleration you can find the velocity. And sometimes you have an unknown in force and you don't know also the acceleration. So you have to go back to the kinematics relation in order to find the acceleration from this relation and then to put it in the Newton's second law. And then from this acceleration, I can find the force. All right. So sometimes, guys, any of the tools learned before may be needed to solve a problem, but what you have to make sure of that you are using consistent positive coordinate directions as used in the equation of motion part of the problem. Alright, so you have to first indicate the positive direction in your coordinate system, and you have to apply this to any equation used in this problem.